Welcome to the Pod of Asclepius, your fortnightly healthcare technology podcast for the technical crowd, sponsored by the American Statistical Association and the Institution of Engineering and Technology. We're bringing the technical experts of engineering, entrepreneurship, data science, and regulation straight to your earbuds. No fluff, no sale pitches, just important technical ideas described well to keep you up to date, all in the time it takes to get to work. And here's your host, Glen Wright Colopy.
Hi everyone, and welcome back to Season 0, Episode 1, Part 1. I thought it'd be good to continue by jumping right in to an episode on healthcare technology, which has the side benefit of further introducing myself as a host. Now, one of the key themes in my work is that a lot of these machine learning methods, no matter how complex, can actually be quite visually intuitive when it comes to creating alarms on patient physiology. So, to illustrate that, this presentation will actually have quite a bit of visual material itself, with figures and videos showing precisely how we can use a machine alarm plus images to demonstrate exactly why a machine learning algorithm is giving a specific type of warning to a clinician. So, if you're listening to audio, maybe just listen to this for a few minutes if it sounds interesting. Hop over to the YouTube or Podbean video to listen to the rest of this episode. If you're already watching on video, just sit back and enjoy. I thought it'd be fun to talk about one of my favorite areas of healthcare technology, which is machine learning and statistics for patient vital sign monitoring. Now, I know there's a lot of buzz around machine learning, AI, smart algorithms, intelligent computation, etc. So I think, first of all, it's always best to step back and ask, where do we want intelligent computational methods? In which areas are they the most appropriate right now? And I was really lucky to have my doctoral work in one of the great examples of a place where we would really like to apply computers to facilitate the tasks of a human clinician. Patients are under continuous vital sign monitoring, like at hospitals and dialysis units or even home care. They all generate these vast digital records. And while a clinician is relegated to assessing patients at only a single snapshot in time before moving on to the next patient, in contrast, a machine can continuously monitor this rich tapestry of information going back to the beginning of the record. And similarly, humans are relegated to very simple decision rules like early warning scores, asking, are the values high, are the values low? As a concrete example, the table you see below is a table for the National Early Warning Score, or NEWS. And the way clinicians make a decision using this information is that they look at a population of patients and decide on discrete thresholds at which they will escalate a particular patient's warning score. So a patient with a heart rate of 90 beats per minute receives a score of 0, whereas a patient with a heart rate of 91 beats per minute receives a score of 1. So these thresholds, although derived from clinical experience and access to population-based distributions, are somewhat heuristically selected, and they revolve around discrete thresholds in order to make decisions. Notice as well that when assigning warning scores, each vital sign is considered only univariately and not jointly across different vital signs. In contrast, a computer algorithm can ask much, much more. For example, a statistical machine learning algorithm can consider correlations between vital signs both across time and across different vital signs. Furthermore, a machine learning algorithm isn't relegated to comparing the patient's current vital signs to a global distribution of patients, because these methods have the patient's own values on hand to provide a unique, individualized source of reference. This allows us to make personalized inferences on a patient's deterioration instead of relying on a global population which has a much wider range of variance. So now, it's worth asking, is current clinical practice good enough? Maybe these simpler methods are more than sufficient to meet our clinical goals. And if they are, we don't need to spend time developing sophisticated algorithms to achieve those goals. Unfortunately, these simpler methods actually leave a lot to be desired. So we want these intelligent computational methods because current clinical practice can't reach the standards of clinical performance that we want for our patients. So we want intelligent computational methods because imprecise clinical practice just doesn't work. And there's plenty of evidence to show this. For example, Oxford University and the University of Pittsburgh Medical Center conducted a study on 332 hospital patients in their step-down ward. And of those 332 patients, there were 112 clinical emergencies that were identified retrospectively from the patient's digital vital sign records. However, of those 112 events, only 7 were actually detected during the study at the time when the patient could have benefited from it. And of those 7, most of them were too late. So if you're a patient on the step-down ward and you're deteriorating, the chance of you getting detected and receiving the treatment that you need is like throwing a dart at the square and hitting the blue part. If you hit the red part, you're out of luck and your deterioration will go undetected. You're at the mercy of your own physiological homeostasis to help you out. Of course, it's not enough just to detect a deteriorating patient. We also need to detect the deterioration while there's sufficient time for appropriate clinical intervention. And we can't just inundate nurses with alarms, because otherwise they'll learn to ignore the alarms. But what I'm hoping to show you is that machine learning methods like Gaussian processes, Kalman filters, kernel density estimates, the real bread and butter machine learning methods that are quite commonly used, nothing particularly sophisticated, can actually be very successful at providing significantly advanced warning while generating many fewer alarms. In contrast, heuristic methods like early warning scores, simple thresholds, provide very little early warning, or even though early warning is late, but have very high false alarm rates that nurses learn to shut off. So plots like this one, which can be read like an ROC curve, help us examine the trade-off between the clinical need for early warning and the hazard for alarm fatigue in clinical staff. So to describe this plot in a little bit more detail, it's good to take an intuition like an ROC curve, where we have these patients who had a deterioration event, and we know the point in time at which the patient deteriorated. So on the y-axis, what we're seeing is the advanced warning of an alarm system in advance of the deterioration event. So if you had a warning 2 hours before a deterioration event, you get a value of 2, and so on. And these are the median values across a set of patients who deteriorated. And the false positive alarm rate, on the other hand, is taking that same alarm system and looking at how frequently false positive alarms came up in patients who weren't deteriorating during that time period. And since early warning is on a continuous time spectrum, we looked in the time period for each patient for 8 hours before they deteriorated until 2 hours afterwards. So, for example, if an alarm went off but only detected the patient 2 hours after their deterioration event, then they get a value of -2. And anything greater than 2 hours after the event was considered essentially missed. So the way to look at this is as follows. The machine learning methods like Gaussian processes and Kalman filters and kernel density estimates, so 2 time series based methods and then an IID kernel density estimate method, both significantly outperform these, providing multiple hours of early warning with relatively few false positive alarms. In contrast, the simple thresholding methods like National Early Warning Score or typical early warning scores needed very high false positive alarm rates before even noticing patients at time. So when we see the green line reaching an early warning time of 0 hours, and it's at already about a 3.5% false positive alarm rate, that means that you have alarms going off extremely frequently just to notice that the patient is deteriorating at the time that they're deteriorating. In contrast, with a much lower false positive alarm rate, these machine learning methods are having multiple hours of advanced warning. And those multiple hours of advanced warning are important because it gives time for the clinician to consider the clinical evidence that's available, combine this warning with other signs of warning and other bits of clinical investigation. And finally, once they have reached a conclusion, there's time to intervene before the patient becomes most dire. And this is interesting because simple thresholding methods are frequently designed by clinicians. So it's a bit interesting that if we have clinical experts who spend time tuning and tailoring their own methods for identifying deteriorating patients, it's strange that a machine learning algorithm, which may or may not know very much about the specific properties of vital signs, can outperform them in this regard. So the question is, how can this be done? What are the advantages that these machine learning methods have over clinical experts? And one of them, of course, is time. Machine learning methods, continuous monitoring, simply have the time to do nothing more than focus on an individual patient and continually calculate and compare to data and make further decisions. But there's quite a bit more that it can do as well. For example, in comparison to a clinician who is only looking at a patient's current vital sign values as displayed by a vital sign monitor, as seen up top, a Gaussian process or some other time series modeling method can actually discern noise from actual vital sign trends to get a personalized prediction about where the patient is going in the future. So whereas if a doctor looks at values, and that value might either be a reasonable estimate of what the patient's average heart rate is at the moment, or it could be corrupted by noise at any given point in time. But they would need to stay around and monitor the patient for an extended period of time to understand what exactly was noise and what were the more average or central values of the patient's vital signs. In contrast, the time series modeling methods have all the data that they need to already be discerning and smoothing over time. So they are more apt for throwing out artifactual data and keeping track of exactly what is the patient's trend. And this is helpful because not only are our expectations with regard to a patient becoming more personalized towards that individual patient, but they're also becoming more empirical because they're based exactly on this patient's data. So taking this further, another thing that a machine learning method could do, for example, are help us transition from making an inference based on a single noisy data point to a distribution of data points or a collection of data points. So these methods are much better at fusing multiple channels or multiple values over time. So in this example that we see right here, what we're seeing is that the Gaussian process method is fitting a confidence bound, you can think of it as a confidence interval over time, to the patient's time series. So we have the average value over time, but we also have the bounds or distribution of that average value over time as well. So it has a confidence range. And once we've fitted the model to that time series, what we can essentially do is we can chuck out the data, but keep that summary information. In this case, we're summarizing the information over an entire time period. And with that shell of information, to be more technically accurate, we're using the Bayesian posterior distribution to summarize the time segment. Then we can compare a more simplified version of the patient's data to other patients in an efficient way. So we might, for example, have hundreds or thousands of previous patients with hundreds or even thousands again of hours of vital sign data. And what we can do is compare the heart rate pattern or another vital sign pattern that we're currently seeing to patients in a dictionary of healthy patients. And if the current patient doesn't look very much like the healthy patients, then what we might conclude is that the patient is not healthy. So the way we might do this, for example, using probabilistic time series, we might be looking at novelty scores, for example, like KL divergence, and showing how far these distributions diverge from what we might expect. And the advantage of this is that whereas a clinician, of course, has seen hundreds of patients, but they've seen hundreds of patients for very brief periods of time before going to the next patient. In contrast, the machine has essentially kept all the information for these previous patients, and it's assessed them retrospectively in an empirical way. So it's keeping the most valuable information, the most important information. And the value of looking at a time series as opposed to one point is that then we can see that we can go from looking at if a patient is unusual with respect to a single point in time to looking at whether or not the entire patient's dynamics are unusual. So if the patient, instead of simply having high or low values, if the patient's vital signs look highly volatile, that's a new piece of clinical information that is harder to incorporate through heuristic practices. So the idea here is that we're able to incorporate more information and pick up changes in physiology that clinicians are currently not looking for. And this is really advantageous because our goal isn't to try to simply reiterate what the doctor's already looking for, but bringing them new pieces of information that they don't currently have so that we can supplement clinical intuition. We certainly aren't trying to replace it. And a great example of how a machine learning method can supplement or even turn clinical intuition on its head is something like step change detection. So in this video, what we're seeing is the Gaussian process continually fitting itself to a patient's vital signs over several hours. So the Gaussian process time series parameters are being learned from the current heart rate values. And when the Gaussian process is fit to the current data, it is also forecasting forward to future heart rate values. So the forecast forward is like this yellow headlight trying to illuminate the future values in gray. And at about hour 33, what we see is the patient has a precipitous decline in heart rate from about 140 beats per minute to about 110 beats per minute. And typical clinical intuition, only looking at individual points in time, would suggest that the patient's getting better because 140 beats per minute is a very abnormal heart rate, and 110 beats per minute is much closer to the population average. So they might think that, the patient is in fact improving. They're converging on more healthy values. But what this step change detection method does is it actually identifies that this is not a healthy event because the change is far too rapid to be healthy. The drop is far too precipitous. And not only is the drop precipitous, but it's sustained over an hour or more. So the values that are falling far out of the expectation are not simply random erroneous data, it's the entirety of a time segment. And a further nice thing about this is the clinician can actually visualize what the machine is detecting and bringing to their attention. So we see the big predictive headlight in yellow. That's where the model suspects that the data should be if the vital signs continue to behave as they have been before. But they can also see that we've highlighted the points that have fallen outside of this range, and that's what we're bringing to the clinician's attention. So in cases where we are turning clinical intuition on its head, providing a very good explanation about why we're bringing that alarm to the clinician's attention. And then with this visualized, the clinician can decide whether or not this is useful information or not. Again, the idea isn't to put all clinical decision making in the hands of the machine. It's simply to identify new things that the clinician is likely to have missed. And once we're happy with these types of methods and comfortable using them in automated settings, another huge advantage of these models is that we can not only use them in real time, but we can actually adapt them in real time as well. So, for example, we might wish to adjust the complexity of a time series model as the patient acquires more data or as the patient's data changes over time. So what we're seeing here is a Gaussian process being fit to a patient's data from when the data goes from being fairly simple, more or less unchanging time series, to having some type of upward trend, to eventually having periodicity. And instead of relying on a clinician or a statistician on hand to manually change or select the most appropriate model for a given patient, we can actually start comparing the model's performance or the model's evidence to decide which model is most appropriate at a given time and switch them out as appropriate. Now, I know the term evidence has very strong meanings in statistics. I'm using it a bit more loosely and a bit more in a layman's sense, that we have the evidence for a model's good performance. So this could be based on something traditional like likelihood, or we could also look at other more bespoke clinical metrics like previous forecasting performance or the clinical implications of decisions derived from those models. And we can use those to compare which models are producing the types of predictions or outputs that we want. And the idea here is that as the evidence for one model being most appropriate changes, that we can switch out the models as needed. Now, of course, this doesn't actually mean solely that every model becomes more complex over time. It could actually mean quite the opposite, especially in acute clinical settings. So, for example, as a patient stays on the ward and becomes healthier, we're acquiring more and more data from them. But at the same time, their data might actually become less erratic, much smoother, much simpler to model. So that's a case where we would actually be acquiring more data, but we could simplify the model because it's more physiologically appropriate. Of course, in other cases, for example, when we're looking day after day, we might notice diurnal changes. So over the course of the day, as the patient goes to sleep, their vital signs follow certain periodic patterns, and that can be captured as well. The advantage, though, is that we have a principled and empirical way to decide which model is most appropriate. By continuously monitoring and analyzing the patient's data, we can also become much more proficient at identifying patient-specific artifacts in the measurements. For example, as seen in this video, we're able to identify and highlight artifacts that we may wish to remove from both statistical and clinical inference. You may wish to rewind the video back for about 15 to 20 seconds just to see as the Gaussian process model identifies erroneous values, and note that the values that they identify as erroneous are not based on a simple threshold on their values, but are very time specific. So an artifactual heart rate value of 100 at one time point is not seen as artifactual at another time point in the future, given the time series context. Now, since the title of this episode mentions the probabilistic elements of these models, I want to take a quick minute to proselytize on how the probabilistic and statistical elements of the methods that we're dealing with right now have an added value beyond what similar non-probabilistic methods would offer. So first, with the statistical time series matching, it would be quite reasonable for someone to say, well, you don't need to really go into the statistical modeling element, because what you could do is simply fit a line through the data using some other type of loss function. And then you can simply compare that fit through the center of the data to other fits through the center of the data. And that's certainly true, you could. Methods like that work fairly well. However, there's a real value in the statistical aspect of each of these, from both fitting the line through the comparison. So when we have these new heart rate patterns, or are trying to derive our dictionary of healthy heart rate patients, we're heavily dependent on the goodness of fit of the time series model to the data at hand. As you can imagine, when we have thousands upon thousands of patients and we are trying to fit thousands of segments per patient, that this must be done in an automated way. And it's the statistical element of that automation that makes it so reliable. So I know that I have waved my hand over the Bayesian elements of most of this model fitting, but the fact is there is significant amount of statistical regularization around the parameters that, for example, allow us to tell the computer how quickly the different vital sign measurements decorrelate over time and how quickly they become unrelated. It also allows us to adjust for the wide variety of noise regimes and measurement corruption that can occur. so that those are actually estimated statistically and incorporated in the fit. Secondly, when it actually comes to comparing one time series to another, there are of course many non-probabilistic ways that you can compare the distance between two time series. For example, dynamic time warping. But the advantage of the probabilistic approach is that we've encapsulated our uncertainty around what that average value is, and the comparison not only includes the distance between the averages over time, but also the extent of uncertainty in those distances. So that's where things like Mahalanobis distance and KL divergence come into play, where we're incorporating our uncertainty in the estimate as well, and that works its way ultimately into the novelty score. Now, for the step change detection method, the non-probabilistic equivalent might be something just like forecasting error. And it's true that forecasting error alone, in fact, forms a very viable step change detection method. In fact, you probably wouldn't want to use probabilistic step change detection if the non-probabilistic equivalent didn't work well. However, the probabilistic approach to step change detection does have performance advantages over the non-probabilistic approach because of the information it's incorporating. So, as you can see from this picture, the patient's vital signs from hour about 33.5 to 34.5 fall significantly away from the expectation, so the thick middle line of the forecast. But as we can also see, they fall very far outside of the confidence interval of that forecast. So that's very strong evidence. But the key thing to remember is that the confidence interval of the forecast is actually derived from our statistical estimation of the noise from the previous data. So it's valuable to have a wider confidence interval in the presence of a patient who has significantly noisier data. You would want to increase that. And therefore, you would not want to keep the same type of threshold for a noisy patient as for a non-noisy patient. And so what the statistical element allows us to do is incorporate that patient-specific noise by estimating it, learning the correlation statistically between time points as they diverge in time, incorporating all that information into the step change alarm. Now, this isn't always easy. As we can see from the step change detection method, there are plenty of instances, for example, between hours 31.5 to about hours 33, that there are strong deviances, probably non-Gaussian deviances, from the model, and this does affect what the mean of the function over time is estimated to be. So these, of course, do come with challenges in their own right to incorporate those statistical elements. However, by having the statistical framework, these are simply providing us with more tools at our disposal to try to encapsulate the specific aspects that we might wish for an alarm system. Finally, for the statistical elements of model adaptation. As I mentioned before, the definition of model evidence has highly statistical and highly probabilistic implications. It's not strictly necessary, but the implications are there, and we can make use of those. Furthermore, when it comes to the actual model selection, someone could of course point out that things like periodic features within a time series are not relegated only to statistical models. There are plenty of non-probabilistic methods that can incorporate periodic features and the like. But the value that I think that we're really seeing here, in addition to our ability to assess model evidence in a principled manner, is that it also gives us a framework, for example, to evaluate the outliers and what to avoid. So when we're bringing things like extreme value theorem from Fisher-Tippett, we can include that information in and decide what to keep and what to discard. And the extent of the outliers and the magnitude of the signals of outliers are highly amenable to that statistical approach in assessing how much we expect individual points to deviate from the population as a whole. So while it's certainly true that the methods I've described above certainly have their non-probabilistic equivalents, and those non-probabilistic equivalents could have quite good clinical performance, there's certainly value added by including the statistical and probabilistic elements that can help us increase our precision. And when it comes to tuning clinical models for real-world performance, we certainly do want to be using every tool at our disposal to make sure that these methods are as robust as possible.
Now, one thing that can't be understated, other than the fact that these methods are not intended to supplant the clinician, but intended to supplement the clinician, is that many of these methods are in fact very interpretable, and they can give the clinician some type of idea about why we're bringing, for example, an alarm to their attention in the first place. A very simple example is the step change method that I described earlier. So here we see Gaussian processes fit to vital signs like respiratory rate, blood oxygen saturation, and heart rate, and the ways in which a step change detector might identify erratic upward or downward movements in an individual vital sign. So here, for example, we see in respiratory rate in figure A that the patient's respiratory rate rapidly increases beyond what the model expects. In contrast, the SpO2 signal, blood oxygen saturation, it drops rapidly. And the cool thing about this is that we don't really need to specify which direction it needs to drop. We're only trying to detect whether or not it's erratic in the first place. In contrast, if we look down at figure D and the values do not change rapidly, then the step change detector won't detect it, and it's quite easy to see why an alarm isn't going off as well. Now, of course, this is not to say that we want a step change detector to be our only source of clinical inference. So, for example, if you had a patient whose heart rate was consistently at 300 beats per minute, a step change detector would not detect that because there's no change. But fortunately, every other piece of clinical protocol would detect something like that. So this is an example of where the machine can provide useful supplements to what is already being investigated in a clinical setting. And there's a very good reason why these step change detection methods are particularly useful and particularly accurate, and that's because they're personalized. The expectation and what they're looking for in the alarms are very personalized to the patient's individual values. And the reason personalization is important is because the interpatient distribution is actually much smaller than the interpatient or population-wide distribution of vital signs. And this is a phenomenon that we can see across many studies, across many different vital signs, whether it's in heart rate, respiratory rate, or if it's a diabetes study that's looking at continuous blood glucose monitoring, where we see that time and time again, if you look at the variability within a patient, it is much, much smaller and much, much more narrow than the variability across patients. And this is important, one, because it informs us that this is an area where machines should be looking to add clinical value by learning those personalized distributions. In contrast, it also shows why simple threshold methods are in fact so challenged in providing the clinical performance that we want. So as you can see right here in the heart rate plot, we see over 200 patients' heart rate values and their distribution of those heart rate values. And as we can see down towards the lower left end, there's many patients who have consistent heart rate values in the 50s and 60s and never exceed beyond 70. In contrast, on the upper right end, we see that there's also a significant set of patients whose heart rates are in the 95, 100, 110 range, and they never go below 90 or 80. And similarly, we have patients in the middle of the range, so patients whose average values are close to the global values, and they also have very confined ranges. So the question is, if you have a patient in the middle range, a patient whose values are average, and their heart rate is significantly higher than what it usually is for that patient, how would you alarm on that based on a simple thresholding method? Well, if you had a high threshold, and for example, we're alarming on 90 beats per minute, well, that means that about a third of your patients would have a constant rate of alarms just to pick up that patient in the middle for the one time they are deteriorating. And similarly, on the low end of the spectrum, that upper threshold would never pick up patients on the low end of the spectrum. So what this means is that there's no threshold that you can choose that can simultaneously pick up the individual deterioration of patients while also having a reasonable alarm rate on a large portion of the patients. Constant alarm rates on 30% of the patient population is not clinically feasible. And as you look across the plots for respiratory rate and SpO2, you can also see that there's no individual place that you can set a single cutoff line that will simultaneously identify an individual patient deteriorating while also not causing constant alarms on the rest of the patient population. So, in essence, the average patient's data is already anomalous to large portions of the patient population. So if you're trying to detect anomalous data, you can't do it by a single threshold. In contrast, using step change detection methods, because the model's already fitting and forming its expectation around the average patient's values at that given point in time. So you're not just conditioning by patient, you're conditioning by the time as well. So there is, in fact, an individual threshold that you can fit for many patients because you're adjusting it to the patient's personalized data. You can identify a patient having a rapid heart rate escalation if their average value is 50, and it's the same as if they have a heart rate escalation, their average value is 90. By individualizing and personalizing the metric, the decision threshold is actually fairly robust across all patients. And of course, it's reasonable to ask, do we really need simple metrics? Do they really need to be interpretable? Would it not be best, for example, for us to have the most complex algorithm that we have, look through the data, decide for itself exactly which patients are doing what, and bring the alarms to the doctor, and we'll just try to max out on accuracy? While the ideas behind that are very attractive, The fact is, it's probably not the best way to go about things, because the alarms generated by a machine learning system are only one piece of a very messy puzzle that is the clinical setting. And clinical settings are, in fact, very difficult, very noisy. So ultimately, the value of adding these more computational inferences to clinical inference only matter in their ability to mesh very well with what's already in clinical operation. So the idea is that it is the clinical practice as a whole that matters. What matters isn't, the cool algorithms or the fancy, beautiful math that's involved in there, or particular metrics that we use that may or may not be bespoke to the current clinical scenario. So there's a bit of a divide there, and that's why I think it's really important that these alarm methods are both interpretable and intuitive. And on the issue of intuitive alarm systems, we don't actually even need models or sophisticated machine learning methods to create intuitive value from the data. So a simple example of this is in the dialysis setting. Now, the dialysis setting, just very quickly, is a clinical setting in which a patient's kidneys are no longer functioning as needed to filter blood and dispense of urine, among other issues. So the patient needs to come in typically about 3 times per week into a dialysis clinic where a machine performs the function that their kidneys normally would. So what this looks like is that the patient comes in, say, Monday, Wednesday, Friday of a week. The days in between they don't visit. So on Tuesday they don't visit, on Thursday they don't visit, and over the weekend they don't visit. And then they come back in the next Monday and repeat the process. And this goes over and over again for about 4 hours per day, 3 days per week. And there's actually a very rich and interesting data sets because you have this longitudinal information both over the course of a dialysis session, multiple sessions per week, and obviously every week of the year for the lifetime of the patient. And there are many really interesting statistical machine learning models that can be applied to this data. However, we don't actually need to go that far to be deriving value. So, for example, if we have the patient's current dialysis session's vital sign values, we can track as they change over time. The vital signs change over time because the patient is having their bodily fluids essentially removed mechanically. And so we can track how that patient's vital signs are reacting to the current treatment and compare it to data that we had from previous weekly sessions. So, for example, the session after the weekend where they've gone 2 days without dialysis might look significantly different than the day that they only have 1 day since the previous dialysis session. And we can also compare it to their non-dialysis days. And so we don't need sophisticated models in particular to summarize where these data were. We simply can visualize it and see where they fall with respect to the majority of data that we've previously observed. Now, something that I mentioned briefly before was the aspect that we can also be taking these statistical models or machine learning models and automatically adapting them to new information. And I think this is a really exciting area because this is where we can take the value of having continuous digital records of a patient and really personalizing the model based on the patient's data. So say, for example, that we want to really tune the step change detection method that we described earlier to an individual patient. So the idea is we want to detect if the patient has an erratic change, but we also want to minimize the number of false alarms that happen because of the step change detector. So the question is, how can we change the Gaussian process model, the time series model, so that it has fewer false alarms and is, by virtue of it being better, able to summarize the patient's data and model the patient's data at any given point in time? The step change detection output might be something like this, where we have deterioration events like the one above, where the forecast is significantly off because the patient has had a rapid fluctuation in heart rate. And those are the types of poor forecasts that we'd like to bring to the clinician's attention, because when the model's forecasting poorly, it means the patient is likely deteriorating. But alternatively, we could also have a poor forecast that would cause a step change alarm simply because the model will fit itself poorly to the data. In a setting in which we are automatically refitting the model, we will always be having this risk. And of course, in the third scenario is the majority of the time when the model fits fairly well and we have a correct estimate. So the problem here is that, for example, we might want to maximize our forecast accuracy while also understanding that there are certain times when an incorrect forecast is actually the correct thing for the model to do. So what this would actually call for then is a more bespoke metric for selecting our models. So, for example, if we're looking to create a patient-specific parameterization of a time series model, and of course, we could then extend this beyond to patient-specific regularizers or patient-specific priors over the model, so that we aren't simply relegating ourselves to a single parameterization of a time series model. We could say, okay, looking back over the previous 24 hours, we have all these different time periods that essentially we could have learned from and provided forecasts in. And what we could do is look retrospectively at different parameterizations and see which ones tended to provide the highest forecasting accuracy overall. Now, of course, we could average across all the forecasting accuracies, or we could summarize the different data points by looking, for example, at a quantile. And the issue with this is, as we make the metrics that we're trying to optimize more and more bespoke to the clinical practice, the challenge there is that we actually then don't have, for example, analytical solutions for what the optimal value are. So this is where, for example, we might want to use something like Bayesian optimization or another non-convex optimization procedure or optimization search procedure to identify optimal parameterizations. So in addition to having a machine learning model automatically fitting to the time series, what we'd actually then have is a secondary machine learning model on top of that, monitoring the first model's performance and then testing different parameterizations to see how it could have improved retrospectively. And so what we see for something like this is that we can have different parameterizations either for the model directly or for the priors or hyperpriors over the machine learning model. And we can test different settings and see which one performed best, and then we can adjust the model in real time based on which one is most likely to meet our clinical needs. So that's a really fun and exciting area because it really encompasses all the different ways that machines can help us personalize medical inference to the individual patient. We can start with using the patient's individual data so that we aren't reliant on global population parameters. But after we've created a personalized model based on the patient's data, we can also further personalize the model by personalizing the search for a more optimal model using the patient's previous values. So that's an overview of one of my favorite areas in machine learning for healthcare. It's patient vital sign monitoring, and the values on these are several-fold. First, machines are essential for providing that continuity of analysis and the continuity of monitoring that no human clinician has time to perform. Furthermore, we can step away from using single data points to make a clinical decision to using the rich tapestry of time series or historical data that provides further context. We, of course, don't need to be using only sophisticated machine learning methods. We could simply just take the data and by plotting and summarizing the data, provide a new source of context. And finally, these methods have a very high potential for future development once you've developed those baseline models, because the inference can only become more complex. You can add more sophistication and more robustness and regularization to the model based on the clinical needs at hand. So this is a fun area. It's an area that has many different research threads. There's a lot of people doing some great work in this area, and one that I'm very excited about. But it's very fun because it allows us both to put on our hat as a scientist, as a clinical expert, and also as statisticians and engineers developing solutions around these clinical challenges.
In part 2 of this episode, I'll continue talking about novelty detection methods, but in this case for identifying artifacts within patients' vital sign time series. Again, thank you for your time. I hope you enjoyed this, and I hope to see you back in the next episode.
Well, that's it for this episode of the Pod of Asclepius. We hope you enjoyed it and will tune in for our next episode. If you're watching from YouTube, don't forget to subscribe to our channel and leave a like. You can also follow us on our other social media channels, including LinkedIn, Twitter, and Instagram. Have a great story or presentation that's ready for prime time? Or know someone who does? Drop Glenn an email because he'd be happy to hear from you. We would like to thank our sponsors from the American Statistical Association section on Statistical Learning and Data Science, section on Medical Devices and Diagnostics, and North Carolina chapter, as well as the Institution of Engineering and Technology. The views expressed on the show are those of the speaker and not their employers, our sponsors, or anyone else not saying the words.